Hi, it's time for another math easy solution. Today I'm going to go over a very interesting video on complex numbers as rotational matrices, and basically show how we could write complex numbers in a matrix format, and then show how it could basically be used to rotate vectors. It's quite fascinating as we dive deep into this. Alright, let's just scroll down here. And also just a note, if you don't have time to watch this whole video, you can play this video at a faster speed. And you can also download the notes and view them on the Hive blockchain in article format and so on. And all the timestamps of all the parts are in the description. Alright, let's dive right in. So let's look at the topics to cover. And note here, the topics covered are listed below and their timestamps will be included in the video description. So we have Fractal Woman and other references. Then we'll go over rotating a vector, and then look at matrix multiplication, matrix addition, then look at the rotation matrix, and then look at complex numbers, and then basically relating the complex plane with the rotation matrix. In other words, we could write complex numbers as vector rotations. And then we could reinterpret or reinterpreting Euler's formula, and then applications to other fields. Just yes, very interesting to think about. All right, let's dive right in. So Fractal Woman and other references. So I got the inspiration to make this video from Lori Gardi's YouTube channel called Fractal Woman, which I've linked below, and here's a link. And I just went to her channel here and I just searched complex numbers so you could see the ones that the videos that she has up regarding them. It's just quite interesting. So yes. And also another note is that Lori herself states that she got this idea from Robert DeCinti from his YouTube channel, and right now the name is www.decinti.com, and here's a link below here. And also I did a search, so you can go to his channel, search complex numbers, and then see those that he has. All right, and now just another note, listed below are some sources which I've used in the making of this video, and this is a SimFiz video derivation, and this is derives the complex number to rotation matrix relationship, and also Euler's formulas over here, Wikipedia, rotation matrix from Wiki, and this is my vectors video on and on the Hive blockchain. I just put the article format there with all the notes, and the links to the videos are in there as well. And here's another reference, matrix multiplication, the Wikipedia pages, and these are Wikipedia ones, matrix addition, complex number, etc., imaginary unit I, and Euler's formula here. Yeah, and most of these are Wikipedia pages because I haven't covered matrices in depth in my channel yet. But anyways, let's go further. Let's look at rotating a vector. So let's consider what happens when we rotate a vector by an angle theta. Alright, so if you recall from my earlier video on vectors, basically we have a vector like this. Let's say we have the xy axis here. This is the x, this is the y. And here I just stretched out the y a bit more. Let's say we have a vector here. It goes from the origin, 0 or O. So let's make it like this. Okay, so this is the vector A. And A with an arrow there. So basically it has a magnitude and direction. The length is the magnitude. And we'll have an arrow on top indicating it's a vector. And then we'll put this kind of bracket, this triangle bracket, x, y. So those are the coordinates of it. Oh yeah, it reaches all the way over to here, and we'll put that indicating it's a vector. And it has a y, and this is let's draw a triangle. It's a right angle triangle. It has a y component here, which equals to, and then we'll say this angle right here is A. So let's say here, this angle's A. Alright, yeah, so that's angles A, and then this y would be R, and let's say it has a radius of, or the length R. This is basically polar coordinates. But here, what this is R times sine of A, and then this bottom part is going to be, well, x equals to, let's move it over here actually, because we're going to need some room. Once we rotate this, x equals to R, the cosine now of A. Alright, so let's say we have this. Now let's say we rotate it, because you're rotating this vector by an angle theta. So it's going to be over across here. So it's exactly the same length R. So let's say it's over here. And this is the length R. And now we're rotating it by theta. Okay, so that's theta there. And this is right here, B equals to Yeah, and we'll call that a vector b. So b is just a rotation of the a, and we'll call this x prime or y dash, like that, just to indicate that it's different from this one. So it's rotating across over to here. All right, so now its components, if I draw this dashed line all the way across here in red, like that, and then draw a right angle sign there. So this one here, so its height is going to be, or its y component, y dash is equal to, or the sine of a plus. Now we combine these two angles, a plus theta. A plus theta. And the next one here, yes, over here, is going to be our x component, x dash. This equals 2r cosine. Yeah, let's write this better. Cosine theta. All right, so we have r cosine, not theta, a plus theta, because the angle is bigger than that. So we've moved over. So a plus theta now, just using a basic trigonomic. Yeah, the concepts or definitions. So basically, we're using a basic trigonomic definitions, and just put a note here. Recall just how we did the triangle setup. Yeah, so recall if you had just a triangle like this. If this is the adjacent is a, this is b, and this angle is theta. Yeah, and the hypotenuse is c, and then basically sine is defined as the opposite over it's defined as the opposite over hypotenuse, so b over c, and then we can move the c over there. We'll get this b equals 2 c times sine theta, or in this case r sine a, and likewise cosine theta is equal to adjacent over hypotenuse, and then we move the c over to the other side, and so on. And then yeah, in that case we'll just get this right here, r cosine a in this case, where r is c and a is theta there. All right, so now that we just recapped on that, now what we have is, let's put these all together. Let's put the all the components together. So thus, we have x is equal to just r cosine a. So that's just x is here, r cosine a. Y is r sine a. Y equals r sine a. And then the x prime, and then y prime, this has the a plus theta. So we have x prime equals r sine a plus theta, and then y prime is equal to r, this is cosine, r sine a plus theta. All right, so now that we have this, I'm just going to box this out just to make it nice, neat package. All right, so we have boxed that out. So now we could simplify this by using the identities for these addition, cosine and sine addition formulas. So recall the following trigonometric identities from my earlier videos. So this is cosine a plus minus b is this link to it, and then sine a plus or minus b. And then basically, yes, we have here. So for cosine plus or minus b, we'll get cosine a, cosine b, then minus plus sine a, sine b. This means basically if you're adding these angles, then we're going to subtract this term. And then sine is going to be a plus or minus b, and then sine a cos b, and then plus or minus cosine a sine b. So in other words, if it's plus here, it's plus here. If it's minus, it's minus. But for cosine, it switches. If it's minus, it's plus, and if it's plus, it goes to minus. All right. So thus, utilizing the addition identities we obtained, and we'll look at this right here. So we're going to look at x prime and y prime. So we have x prime is equal to r times cosine a plus theta. All right, now we can just plug this into that formula here, and this one here I derived both in these two videos. So yes, make sure to watch that if you want to see the proof. So then this becomes r. We're going to get r times it by cosine. Now this is a is this a, and then b is this theta there. So we'll get cosine a, cosine b, cosine theta. Then we're going to go minus, because it's plus turns into a minus for the cosine identity. All right, and now, yes, minus, and then we're going to do sine a cosine, just sine again, sine theta, like that. And now, here, we also need the r in both, because you get to expand that out. Yeah, so the inside will be there, and we also have to have that r there, because we just FOIL it out. There's going to be an r there. All right, so now what we have here is, well, if you notice, this part here, r cosine a, that's just this part here. That's this. R cosine a is just x. So this equals to x. Now this one here, r sine a, this equals to y. That's y. Let's erase these. So yeah, those are just y, r sine a. So in other words, this equals to x cosine theta minus y sine theta. All right, so now let's bring this down and write x prime and then box this out. So that is a very interesting formula. Yeah, so basically, in this case, we don't even need to know the angle A. We just need to know the coordinates here, and then basically then we'll have this theta there. But you could always solve for the angle A if you know these two. So they're using basic trig. So then we'll get, just a formula in terms of x, y, and then this theta there to get the rotation vector there. So we rotate it over here, and we can get the components accordingly. So that's for the x. Now let's take a look at the y one. So y prime is the sine one. So y prime equals to r sine a plus theta. All right, so that's the r sine a plus theta, and just make this theta nicer. All right, and now what we'll get is for the identity, so sine a cos b, and then plus cos a sine b. So this equals to r times it by sine a cos b, which is theta, then plus, and we're going to get a cos, or multiplied by the r. So cosine a, and then sine b, or theta. And that is what we get there. And now likewise, this part right here, this is our sine a, that's just our y. This equals to y. Now this equals to x. All right, so now let's put this together. Yeah, so our cosine is x, and we'll put the x component first, so we'll put x. Notice the difference. This one's cosine on the top, this one's going to be sine. So x sine theta. X sine theta. And then we're going to have a plus, and then we'll write this one in a second. So y cosine theta. Cosine theta. And notice the r is gone. Yeah, there's no, so we just replace the r. If we know x and y, we don't need to know r or theta. I mean, or a, the angle a. So then this is going to be, bring this down, and we got a nice, neat little equation here, y prime. All right, so now we have this. All right, so we have this, and remember, these are just the components of the same vector that's rotated by an angle theta. So that's rotating a vector. All right, so now we have that under our bag, and now let's look at matrix multiplication. So a matrix, plural is matrices, is just a rectangular array or table of numbers, symbols, or expressions, such as the following 2x2 matrix. So here's just a matrix that has 2 rows and 2 columns. I'll call this A inside here, B, C, D. So this is 2x2 matrix like that. All right, and that's pretty much all a matrix is, just a table or array of data points. In this case, there's 4 for this 2x2 matrix, and you could make them whatever you want, and so on. So now let's take a look at multiplying 2 matrices, such as A and B. This is defined such that it produces a second matrix C, and it is denoted by AB and follows the rules listed below. So the number of columns of the first matrix A must equal to the number of rows in the second matrix B. And the resulting matrix has the same number of rows of the first A and the number of columns of the second matrix B. So it's the same as the second matrix B columns, and then the other one A rows. And MES note, typically the notation for matrix is to bold the symbol such as A, but I'll use the following notation as well, where it is more clear with this rectangular bracket and bold. We'll have like this bracket A and an end bracket. And this notation, this one Lori Gardi uses it, and she also got it from DeCinti, Robert DeCinti. Yes, which is quite interesting. And let's go now and illustrate these rules, or this multiplication, but mainly these rules that we are defining for multiplication. So let's say we have a matrix that's this much rows. We'll call this, say we have 5 rows. We'll call this I. Because I is 5 rows. We'll call this like that, I is 5. And this is, we'll go here, 1, 2, just 3. So this is going to be 4. This is going to be 5. We have 1, 2, 3, 4, 5. 5 rows, like that. Let's erase this. Erase, 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 erase. So that's 5. And let's say we have 3 columns in this first one. All right, so that's our first matrix. And this is 3, 1, 2, 1, 2, 3, and so on. And this is going to be, let's call this M equals to 3. And this is our matrix A, like that. And we're going to multiply this matrix A by B. So now let's look at the first rule, the number of columns. So this is the columns. Yeah, this right here is the columns. M is 3 of the first one. So the number of columns of the first matrix A must equal to the number of rows of the second matrix B. All right, so then these ones have to match with B. So in other words, we need an M is 3. So we're going to have 3 right here. So 1, 2, 3 rows for the second matrix B. But otherwise, we can't multiply it according to our definition. And this is going to be, we'll call this also going to be M is 3. So that's the second matrix. And there's no other rules for the length of this one. So we'll make this 4, just so it's different. So we'll call this 1, 2, and then there's 4 now. Yeah, that means there's 4. Whoops. Alright, so this is 1, 2, 3, 4, like that. So there's 4, and we'll call this N for the number of rows of the second. This equals to 4. And this is our B. So A matrix times B. This has to equal, now let's take a look at the rules. The resulting matrix has the number of rows of the first A. So in other words, this has to have I is 5. And the number of columns of the second matrix B. Number of columns is 4. So in other words, we're going to get I5 and we're going to get N4. So we're going to go here. This is going to be 1, 2, make this longer. 1, 2, 3, 4, and this is going to be like that, like this, and like that. And here's, fix it up, moved it around. So that's 4. So we go 1, 2, 3, 4, and it's 4. And then we have I is 5. So 1, 2, 3, 4, 5. And this is going to be I equals to 5. So this is equals to our C, or AB, like that. So yeah, that's our C matrix there. All right, so now that we've gone over these rules for the size of these matrices when you multiply, and the rules that you need these ones to be the same. So this needs to be the same here, and then the following one has the lengths accordingly. So the rows of the first, and then columns of the second. And now we'll look at the rules for the actual values inside this matrix C. So the values in C, or AB, involve multiplying each corresponding row of A. So we'll look at the row of A we get with each corresponding column of B and summing them up as follows. All right, so to illustrate the rules for the values inside of this, we'll look at a simple matrix. So we'll look at a 3 by 2 times by 2 by 2. So in other words, the first one, let's use 3 rows. So I is 3. And what I'll do is, well, it's going to be 3 rows. So the first column is going to be, we'll label it such as this, where the first number, 1, indicates the row, and the second number indicates the column. So A11. And then this is going to be 2 now, because it's the second row. A21, still the first column. And this next one's going to be A31. And then we'll use just a 2 by 2. So, a 3 by 2. So then the next one's going to be, well, first row, second column. This next one's going to be second row, second column. Next one's going to be third row, second column. And this is going to be M is equal to 2. So if M is 2 in this example, if we're going to multiply by another matrix, it needs to be the same. So M needs to be 2 as well. For the rows. Yeah, for the rows. Times it by, and then we're going to have the M is 2 as well. It has to be M is 2. And let's say the first one's going to be, let's use B now for this matrix. we'll call this B11, first row and first column. Second row, first column. And then let's just use a simple 2 by 2. So then we'll just stick over here. So B1, first row, second column. Second row, second column. So B22. B11, B12, and B22. And this is just our n is equal to 2. So now if we multiply, when we multiply, we're going to get, well, number the same. We're going to get I, if this is I equals 5, this is I equals 5. So in other words, it's going to be 3. It's going to be 3. I equals to 3. So 3 rows. And it's going to be, then it's going to be n is 4. N is 4. So n is going to be 2 columns. And the values inside, they're going to be, well, according to this, these rules. So multiplying each row of A. So we'll take a row of A. And then by the column of B. So this is a column of B, like that. So, and they're going to be like this. So A11 multiplies with this one here. So this multiplies with this. And we're going to get A11 times by B11. And then we sum them up. So then we sum up. In other words, this is going to be added to, and then the next one. A12 times by B21. So these are the rules for matrix multiplication. And it's going to be B, or A12 times it by B21. Yes, so 21. So the rows and columns. And that is basically the pattern we're going to have to follow for every single setup here. So that's the, so that's the corresponding row with the column. So that's the first column. So this is just one data point there. All right, and here's move things over to the left just to get more room for the second column. So that's the first one there. And then the second one's going to be, well, we're going to multiply now this row by this column. So in other words, we're going to get A11. Again, I'll just do this one last time for this, just to illustrate this. So A11 multiplies with this, A11, and then B12. And then we're going to get this multiplied by this. And then plus, this is going to be plus A12, 12, and then B22. B22, that's right. And I'm going to move this a bit closer. And we're just going to box that in. I'll draw the box here. All right, here, let's move this over. And so that's the first one. And so we got the first two columns of the data on this one here. The first two columns of the first row of this matrix here. And again, I'll put this here. N is equal to 2. So the same as this one here. N is 2, I is 3. This is the number of columns. All right, let's go back here. So now the second row is basically going to use this row. And again, the columns. That's why the number of rows here match this one, and number of columns match the second matrix. And then we're going to multiply that again. So it's going to be A21 times B11. A21 times B11. And notice the pattern here. So this A11 is B11, and then the next one's going to be B21 as well. And this one's going to be just A22. So plus A22. And then this one here, B21, like that. And then the next right here is going to be, now we remove this, and now we're going to multiply by this side. This one stays the same because it's the same row. And this is going to be A21, B12, and these ones always the same on these ones, plus A22, then B22. All right, so matrix multiplication, or just matrices in general, aren't that complex. They're just basically repeating a whole bunch of tedious calculations into a compact form. So that's pretty much a matrix algebra. And when you go do linear algebra and so on, it's pretty much the idea of it is to streamline so it'll be easier for computers to do. All right, so now we have that. And then the next one is here, A31, A32. This is the third row. And then we'll look at the first column of the third row, multiply this. So A31 multiplies B11, then A32, B21, and so on. So notice these ones all match. So we could just simplify this whole thing, B11, B21, because that's going to happen. And then this one here, all of the same ones that are exact, so B12, and this one's B22. Those ones aren't going to change, and then we'll multiply this inside here, A31, and the next one's A32 plus A32. And then this one here, notice this one's the same, the rows are the same, and then this one here, the columns are the same. So notice the symmetry there, or the pattern. So the next one's going to be just A31. Move this here, multiply by that in here. A31 plus A32, like that. All right. All right, now that we've covered matrix multiplication, now let's quickly look at matrix addition. This one is easier, or just simpler than this. So matrix addition requires that two matrices have equal number of rows and columns, and the result is that each corresponding entry simply adds up together, as the following example illustrates. So basically, two matrices have to have the equal number of rows and columns. So they need to be the exact same size. So in other words, if we have this right here, so this is how it's defined. So if we have A11, we'll just do it simple 2 by 2, and we just add up each corresponding one. So this is A11, A12, and A21, A22. So the second, so remember, the first number is the row, second one is the column. So A11, A12, or first row, second column. And multiple or added by, we're going to add this to second matrix B11, B12, B21, B22, like that. All right, so now this equals 2, and then basically we're going to add up each corresponding entry. In other words, this adds up with the corresponding one because they're the exact same size. So this is going to be A1, and it's going to be the same size, both 2 by 2. So A11 plus B11, like that. And the next one is going to be A12, adds up with B12. So yeah, this one's much simpler than multiplication. A12 plus B12. And then likewise here is going to be A21 plus B21, and then A22 plus B22, like that. Alright, now that we've covered addition, because we're going to use this later on in the video, now we'll take a look at rotation matrix, or rotation matrices. So now let's get back to our earlier vector rotation and summarize what we have. So if you scroll back up and take a look at here. So this is what we have, and then we wrote it down like this, and then we solved for these values, these x prime and y prime, those are the rotations. So let's just summarize what we have and the fundamental stuff that we covered. And so what we basically had was a rotation. So we had, this is the xy axis, x, y is the origin, and let's say you have a vector here, A, and this has components, write this in a triangle bracket indicating it's a vector, x, y, and then we rotated this and put it like this, make it a bit longer. Yeah, so we rotated it by an angle theta. We rotated counterclockwise, so we'll have the angle, the vector B with components x prime, y prime, and let's write this here. Actually, let's put it all as compact as we can. Where x prime is just going to be x cosine theta minus y sine theta. Well, actually, it's gonna run out of room there. I'm just gonna move it over here. So I wrote it down actually here. So here I just moved it down over to here. So this is the x prime equal to x cosine theta minus y sine theta. Again, let's double check that. So we have x prime is equal to x cosine theta minus y sine theta, and then the y prime is x sine theta plus y cosine theta. All right, so we have that, and then we're gonna get y prime is equal to x sine theta, and then it becomes a plus y cosine. The cosine sine switch sides in this case, and then we're gonna have a plus instead of a minus. Alright, so now that we have this, we summarize what we covered, and now let's apply the matrix stuff that we learned, the multiplication and addition and so on. But first, let's try to convert our vector rotation into an equivalent matrix form. So here's our vectors, and let's say what we have. Let's say we have our first vector A. A like that is equal to, we'll put a triangle bracket indicating it's a vector. So you can write in this notation, but let's write this as a matrix, and this will write this as a basically a 2 by 1. We'll write this as an x, y, and put it like that. So that's a 2 by 1 matrix, like that, or 1 by 2, depending on which one you're counting first. So yes, 2 rows, 1 column. And for I just added clarity, I equals to 2, m equals to 1 here. And yeah, well, that's pretty obvious. So I'm just going to erase it. So that's a matrix there for it. And now the b vector is over here, x prime, y prime. It is darker. So this equals to, and component form, x prime, y prime, and in matrix form, this equals to x prime, y prime. All right, so now what we have is, well, I'm going to write, now we have this. I'm going to take this and write this out or expand it by itself. I'm just going to put x prime, y prime, and plug in the actual values for them, or the formulas that we have. This equals to, in a 2 by 1 matrix, this right here, x cosine theta minus y sine theta. So this is going to be x cosine theta minus y sine theta. Yeah, sine theta like that. And then the next one is, this is going to be x sine theta for the y prime plus y cosine theta like this. All right, and now what I'll do is, well, I'm going to put the x on the other side. So we're going to have a matrix, yes, we'll have the cosines in the front. I'm just going to switch them over. So we'll write this as cosine theta times x, and then minus sine theta times y. And then this one's going to be sine theta times x plus cosine theta times y. We did that just because we're going to have a matrix, a bigger matrix in the front, the rotation matrix. We'll illustrate that in a bit. Cosine. All right, so we have this, and now what we can do is break this down into a matrix multiplication. So notice right here, in this case right here, we have the rows is going to be m. We'll call this I. Yeah, I is 2. And then it has n is equal to 1. Because these are just a subtraction. So, but it's actually just 1 there. And then this, what happens is this equals 2. And we're going to need, so if the number of rows is 2, so we're going to multiply it. Let's go back to our setup here. So we have a setup like this. So we have, this one has to match the first one. So we're going to have a 2 row. And then the second one, the number of columns must match the second one. And then this is going to have a row of the same here. Like that. So in other words, we have to have I is 2, like that. Yeah, let's put this like this. I equals 2. And then this is n equals to 1. And we're going to have to, when we multiply it by, you're going to have to multiply this by something with the same. This is m. We're going to have m. Then we're going to have n equals to 1 there. So it matches that. So let's just start off with what we have here. Well, it should be pretty straightforward. We just look at this right here. Let's just take out the cosine theta and this y and this sine minus sine theta, and put that as we'll just look at 2 by 2 matrix actually. And then the next one, sine theta. So yeah, this is pretty straightforward. Like that. This is going to be our m is equal to 2. Yeah, here I just move the things around and move this here actually. I equals to 2 here, so it matches up with this. Or just the same method we were using. This is going to be m equals to 2. And then you multiply this by, well, it has to have m equals to 2. And this is just our x, y vector, and this is n equals to 1. So this matches, and this match. Yeah, so that's pretty interesting. They all match up. All right, so yeah, so that is what has to happen. And when we multiply this out, well, we obviously get this. So we multiply the rows by this. In other words, put the x in here, and then the y, and we just get this. Yeah, let's just erase that. So yeah, it's pretty straightforward. So, yeah. The next one is multiply this by this. Is basic matrix multiplication as we defined above, and we're gonna get the sine theta, cosine theta. Yeah, so this this x and this can be y. So that's this part, and this part right there. Yeah. So in other words, what we have is erase everything. Whoops. No, actually, no. That, yeah, that's right. So this is what we have, and let's sum this up and write this out. So thus we have the rotation, vector rotation, as a matrix multiplication. So x prime y prime equals 2 cosine theta. Let's write this better. Cosine theta minus sine theta, and then we'll have a sine theta, then we'll have a cosine theta, like that, and multiplied by x, y. Now this is absolutely fascinating. All right, and now let's just box this whole thing in. So we have. All right, so now that we have this, and now let's go further. So the above 2x2 matrix, this one right here, this setup right there, is called the rotation matrix, which we denote by r, or r as a function of theta, since it rotates the vector a by theta. So in other words, r, the rotation matrix, is equal to, well, r theta, which equals to, I'll just put r like that, because yeah, but sometimes I'll use the r theta when we put in a value for theta. It's going to be cosine theta minus sine theta, then sine theta here, cosine theta here. All right, now that we have this, and we have basic rotation matrix under our belt, let's jump right into complex numbers, and then we'll go over a relationship between the two. So note that I had done a video on complex or imaginary numbers 11 years ago, but it is a bit outdated and unpolished, as it was one of my first videos on the channel. You can see the difference 11 years makes. So there it is, like that, and this is all in one page like that. Yes, very interesting stuff here. So December 21st, 2011. Very, very epic. Yes, a lot of upvotes there. Apologies for that. Anyways, let's jump right in. So let's start. Yeah, so let's now start fresh here, because this is just not as clear. So a complex number is an extension of real numbers by using the imaginary unit or imaginary number unit I. The imaginary unit I is a solution to the equation. So if you have the equation x squared plus 1 equals to 0. So real numbers can't solve this, because when you square, you always get a positive number. So in other words, if we move this over, let's just move it over, and then what we get is, and then we're going to get, I'll just move that over, then we get x squared equals to -1. And then because you can't use a real number, so we'll just say the number is I. So I squared is equal to -1, like that. Or you could square both sides, and we're going to get I is equal to, well, plus or minus square root of -1. It'd be plus or minus because we're doing a square root. Yeah, when you square root, it just means you're multiplying two numbers to get this square there, and then when you multiply two negatives, those cancel out and becomes positive. So it's similar to just the positive becomes positive and negatives become negative. All right, so that's plus or minus like that. Just move this over here. And yeah, so because no real number satisfies the above equation, x squared plus 1 equals 0, I was called an end quote imaginary number, and still is called that in many places. So complex numbers are written in the form, yeah, so that's an imaginary number or imaginary unit number unit I. So yeah, it's Wikipedia just says imaginary unit now for some reason. So anyways, I've always called it imaginary number. So complex numbers are written in the form z equals a plus bi, where a and b are real numbers and I is that imaginary unit. The a term is considered the real part, and the b term is considered the imaginary part. Yeah, so the real one is this a, and this, even though a and b are both real numbers, it's just indicating that a is for the real part, b is the imaginary. A complex number can be visually represented as a pair of numbers a and b forming a vector on a diagram called an Argand diagram, where the imaginary axis, we'll call that IM, is the vertical axis, and the real axis, RE, is the horizontal. Yeah, so in other words, basically a complex number is just a two-part number instead of just one. So let's just draw this out. So if you have, make this a bit bigger. All right, so we have, this is the real part, we'll call this RE axis. There's the imaginary IM, and this is the origin. And then you have a vector here, and this is a vector is a complex number, so it's going to be called Z is equal to A plus B I, where the components are A is the real part, and then the vertical part is the imaginary, or B. And so it's not imaginary, it's just saying that there's a second part to it. So each number will have a second part of this number. Yeah, and an example of adding such a second part or property is, for example, let's say you had all the real numbers, and then you assign a color to all of them. So you could be like all the real numbers that are blue, red, etc. So instead of saying they have an imaginary property, we'll just say no, they have color, for example. Yeah, so in this case, you're just adding another property, and you're graphing it on this axis. This is called imaginary axis, and so on. All right, so let's go further. So now let's break down the complex number z into its component parts via the angle theta, and only consider the unit length of 1, since we only want to consider rotation for now, so we don't want to deal with the length and so on. We just care about the rotation, etc. from this axis there. So let's write this out. All right, so let's draw the imaginary and the real. This is the real. This is the imaginary IM. And now we have an origin right there. And so let's say we have the unit length here. So unit length is 1. Just 1 to be easier to deal with. And this is our z equals to A plus B I. All right. And then this is the angle theta. So from the real axis. And this is going to go down like that, dot. And now these components are, this is the B, this is the vertical. So it's a vertical component, and that just makes it with the, well, the hypotenuse there is 1. So we just do 1 times sine theta, or just sine theta. And then A is equal to, well, cosine theta, as before. All right, so that's, we have that. All right, so that's for this unit length complex number. Z is equal to A plus BI, or this equals to, well, cosine, A is cosine theta, plus B is sine theta, I. So in other words, we have Z like that, and box that in. Alright, so now that we have the complex number here, the unit complex number written such as using these components cosine theta and sine theta. So now we've gotten here, we've gone over the matrix and rotation matrix. So now let's rotate or relate all of them all together. So relating the complex plane, which is basically the set of all the complex numbers over here, with the rotation matrix. So let's try to manipulate our previous rotation matrix equation to try to get it in a form similar to the above complex equation. So this is the complex number. And now let's take a look at the R matrix. So here R equals to cosine theta. This is the matrix. Cosines on these column, or on the forward diagonal, and the sines on the opposite diagonal over there, on the backward diagonal. We'll call that backward diagonal. All right, and then there's the -1 for this sign there. So let's just write this down and try to break it down using our matrix addition setup. All right, so we're going to have R equals to cosine theta's on the top, and cosine theta's on the far column, and then we have a negative sine theta, just notice the pattern, and sine theta, like that. All right, so what we could do now is we can manipulate this setup using our addition setup. Remember, when we do matrix addition, we just scroll back above here. So matrix addition, basically, these are just added terms. So we can separate this big one into separate ones here. And to do that, what we'll do is notice the pattern here. So we have the cosine, cosine. We want those in its own matrix, and the sine and sines in their own matrix. So what we could do is write this out as cosine theta, and then this one's 0. This one's 0. This one cosine theta. So in other words, we have that, and then what we're going to do now is plus, and then we're going to take only the sines now. 0, and it's going to be negative sine theta, and it's going to be sine theta, it's going to be 0. Like that. And we could see basically by a matrix addition, well, this would just get the above setup here, because we would add all the corresponding terms. So cosine theta plus 0 is just cosine theta. And then 0 plus negative sine theta, just get this, etc. So this is just same as this up top. And now what we'll do is we're just going to factor out the cosine, because then, yeah, when you have a constant there multiplied inside a matrix, you just put that in every term. So we'll multiply or factor out this cosine theta out of there. And now we're going to be left with 1, 0, 0, 1. When you multiply cosine inside, you just get the cosine on the diagonal there. And the next one's going to be sine theta. So take out the sine. And we're going to be left with a 0. All right, put this like this. 0, negative 1, 1, 0. Like that. All right, so now let's call this matrix right here. I'm going to call this I. This is called an identity matrix whenever you have a diagonal forward one like this with all ones and everything else 0. And I'll put the bracket on top just so it's more clear that it's a matrix. And this one here, I'm going to call this X. Because we don't know what this is yet. Let's put that as X with a bracket indicating it's a matrix. And what we get is, let's put R, well, R equals to, let's put this here in this notation, matrix like that, because we have this cosine, it's not a matrix. And then I, and then plus sine theta X. Like this. And yeah, so this is what we have here. I'm going to put this all the way here, and I'm going to box this out. All right, so we have the rotation matrix equals to cosine times this I matrix called the identity matrix, and then plus sine theta times this X matrix right here. We'll call that X. Like that, because it's this one is identity just because it's 1 across there. This one has a negative 1 there. That has interesting properties. So let's go further. All right, and here, yeah, just added a note. Note that the I matrix here, or I bracket inside the bracket, a matrix above is called the identity matrix. Let's put this in bold. So let's compare our above expression. So this one here with that of the complex number or unit complex number, just a unit length one. Yeah, complex number equation we derived earlier. So compare that with this setup here. All right, so that's z equals cosine theta plus sine theta I, and this one's here. So let's write this out. I'm going to write this in this notation. R matrix equals to cosine theta times by the identity matrix I plus sine theta, and then X as a big one. Just put a big X like that. Versus, I'm going to put this as right here, VS. I'll put this here versus, I should put it here, VS. Versus the complex number. The unit complex number Z equals to cosine theta is by itself. So just cosine theta, but I'm going to put a 1 there. I'm going to put times by 1. This one times by I. Times by 1 plus sine theta times by I, like that. All right, so these look very, very similar. Now let's compare the properties of, well, 1 and I. So let's compare the properties of I and X with that of 1 and I, the imaginary number or imaginary unit. Yeah, so what I'll do is I'll look at this I and let's square it. So if we have I, yeah, I or bracket I squared, this equals to, well, this is number the I, the identity matrix. This is 1, 1 on the diagonal, 0 everywhere else. And let's square this. In other words, we're going to do matrix multiplication. So if we square this, All right, here's fix that up. Squared, this just equals to, well, just matrix multiplication, 0, 1, times it by 1, 0, 0, 1. All right, so again, matrix multiplication, so we just multiply this, the row, with the column. We go 1 times 1 plus 0 times 0. So in other words, we get a 1. And the next one is, and also these are the same size, so the resulting matrix will be the same as well. And the next thing we're going to do is, well, this is going to be a 1. Next one is the first row in the second column. So 1 times 0 plus 0 times 1. In other words, we get a 0. And then we shift it over to here. And this row. So 0 times 1 is 0, plus 1 times 0 is 0. And then the next one, we get 0 times 1, and 1 times 1. We get 1. All right, in other words, we get back to our identity matrix. So this equals to I. So in other words, we have I squared is equal to 1. I mean, I squared is equal to I. Like that. It's quite amazing. Versus, now we'll compare it with VS. Compared this with the imaginary number, I squared. I mean, not I squared. Yeah, the imaginary number is just 1. I mean, not the imaginary, this one here. Compared with 1. So this is the identity matrix. Let's compare the identity number, or just number 1. 1 squared is equal to, well, it's 1 times 1 equals to 1. So then these check out. So I'll do a check. So these work the same. So now that's the first one. And let's check x squared. So let's do this x squared. So this one, x is 0, -1, 1, 0. So let's do that. X squared is equal to 0, -1, 1, 0. This equals 2, and then we're squaring it. So then this equals to 0, -1, 1, 0. Multiplied by 0, -1, 1, 0. This equals 2. And here I just move things around so it fits. Now do the matrix multiplication. So this row and this column. So 0 times 0 is 0, plus -1 times by 1. That's going to be -1. Now the next one is the first row, second column, like this. So we go 0 times -1 is 0. -1 times 0 is 0. So those add up to 0. And then the next one is over here. Over here and here. And, no, that's the column. This row, column. 1 times 0 is 0. And then plus 0 times 1 is 0. And then the last one is here. 1 times -1 is -1. Plus 0 times 0 is 0. So we get a -1 here. Yes, in other words, this is just, well, negative I. Remember, this is just 1, 1, so we put a negative in there, it just becomes -1, -1. Yeah, so this, is equals to -I. So in other words, x squared is equal to negative I, or the negative identity matrix. Like that. Alright, yeah, so notice the similarities, and first I'm just going to box this out. And so box that, and now compare this with the, well, VS. The I squared equals to, well, -1. Yeah, which is, this put over here, which is that imaginary number setup. And this is, I'm just going to box this out like that. And this checks out. Compare that with this. In other words, this checks out. So this, and notice they're exactly the same. This has the same property. When you square this, it's still 1. When you square this one here, you get negative of the identity matrix. And this one is, similar to this one. When you square the i's, it becomes -1. So this is some interesting stuff here. And this deserves a hashtag. Wow. I was actually blown away when I found this out. Alright, yeah, so thus we could say that our rotation matrix is equivalent to an unit complex number. Hashtag amazing. So what we can do is write this out as R. R equals to cosine theta, cosine theta, negative sine theta, sine theta. Yeah, here's fix that up. And now this equals 2. We could write it in this format, cosine of theta times by the identity matrix. I'll put this in the bracket like that. I plus sine, and then the random x. Let's put an x matrix. And now switch over that x and put this as cosine theta, identity matrix I plus sine theta, and now we'll call this, I'm going to put this as lowercase I. In other words, it's an imaginary number, but as a matrix. So it's just this right here. Just this right here. That's just I as a matrix form, as a rotation matrix. All right, so we have that. In other words, and now we know that in the complex plane. So when you go back to the complex plane, yeah, this complex plane right here. So number A is cosine, B is sine. So in other words, this just equals to A identity matrix plus B, and then the I matrix. All right, and I just want to make a note. This is typically used for the identity matrix, the capital I. But another way possibly is look at just a 1 with a bracket inside, but then that probably adds other confusion. But just to match up with this here. But nonetheless, capital I has a good symmetry or pattern on its own, because so capital I indicates the real number part, and then the lowercase I is the imaginary one. So anyways, again, this is for the unit complex number length. And now you could write this again. This is the identity matrix, and there is the imaginary matrix. And then when you plug in those inside, so then the cosine, sine, etc. This is cosine is just A, sine is just B. So we could write this as a matrix: A, negative B, B, A. Yes, absolutely fascinating stuff. So there's a whole bunch of ways of writing this matrix, rotation matrix, and relating it to equivalent form of the complex number as a rotation matrix, which is quite amazing. All right, so now that we have this relationship here, let's continue further and now look at complex numbers as rotations. So the identity matrix I, I, and the imaginary or the unit, I'll put unit here. And the unit matrix I can be, unit imaginary matrix I can be viewed as rotations of 0 degrees for the I, the capital I, and this is lowercase I, and the 90 degrees, and 90 degrees for lowercase I. So remember, we're dealing with a rotation matrix. So note that, or recall that at theta equal to 0, we have cosine 0 is just equal to 1, and sine 0 is equal to 0, and I'll illustrate this in a bit. So thus, what we have is R of theta equals to 0 of a rotation matrix. This equals to, well, cosine 0, negative sine 0, sine 0. Sine 0, this is cosine 0. So in other words, we get a, we get a 1. I'll put this actually lower. Let's put this right here. This equals to, well, cosine 0 is 1, sine 0, negative sine 0 is 0, 0, 1. Now this is just the identity matrix, like that. And now just recall, just a quick recap. Recall trig functions, or how they are. So if this is the angle theta, this is y, and this is our sine. So sine looks like that, where this height is 1, this is negative 1 here, all right, and then this is at 0, the origin, 0 there. So that's for sine, sine theta. So at sine, at theta is equal to 0, we get 0. So that's how it looks like. And then if we draw in red, it's going to look something like this. Red looks like this. This is a cosine one. All right, so this is cosine. Here, just put that arrow there. This is cosine. Cosine theta. And notice how the value is 1 at the origin. So we have 1 there. So it looks like that. And there's the 1, 1. Yeah, so that's what we have. All right, so let's continue further. So this is, yeah, for the identity matrix. Now let's look at the imaginary matrix. And this one is at 90 degrees turn. So at theta is equals 0. And then this one now, if we look further, at theta equals to 90 degrees, which is just equal to pi over 2 radians. So in the different units there, radians. What we get is cosine. Yeah, so we get cosine pi over 2. Yeah, cosine pi over 2. This equals to 0. That's this value right here. This is at pi over 2. So that's cosine pi over 2. And then the sine becomes 1. And then sine pi over 2 equals to 1. All right, so thus, if we plug this into our rotation matrix formula, so we get thus, yeah, so thus R of, put this here, R of theta equals to pi over 2. This equals to, yeah, so this is theta equals 0, this is pi over 2, we're dealing in radians. And this is going to be cosine pi over 2, negative sine pi over 2, sine pi over 2, and then cosine pi over 2. This equals 2, plug this in, we get 0, negative 1, 0, I mean not 0, sine is 1, 0, like that. And this is, again, that's just our imaginary matrix. I'll put it like that. You put it like that, or just leave it as I, because we're dealing with matrices, so it's pretty straightforward here. Yeah, so we're dealing with that. Just similar here. I just put the without the just put the I, capital I, without the brackets, because it's pretty straightforward. But yeah, might as well just box these in. I'm just gonna box this in because it's we just solved that out, and this equals 2, and solve this out. All right, going further, so now that we have these as angles, or just rotations there, because we plug in the rotation angle inside this rotation matrix, and we get our identity or imaginary matrix. So equating unit, again, I'll talk about the unit there, because it's length 1. Unit complex numbers to rotation matrices effectively means that we can interpret complex numbers or unit complex numbers, because if it's not the same length, I think there's going to be some stretching involved and so on. So unit complex numbers as applying a rotation to another vector. So, yeah, so we're going to be, if you look at a vector here, say we have x, this is the origin, the y, like that. And let's say we have this vector A. Like that, that's a vector. And then we're going to have, and then you rotate it by, you don't stretch to make it exactly the same. Rotate it by, let's make this a bit longer. One more try. All right, that's perfect. All right, it's rotated by theta. So this vector B is equal to the rotation matrix R. We'll put this theta there just because we're using that exact angle. And then put that in brackets so it indicates the matrix, times by A. So you rotate it across. So that's, you could view that as complex numbers. All right, so this is a generic angle, theta, but if we want to rotate by 0, that's just multiplying it by 1, or I. So this means that, put it like this, make it bigger here, move it down here. And we're going to put these two together. So we get, this is the origin, this is the y, this is the x. Like that, and now this is a vector, and this is vectors A, and this angle here, theta is equal to 0. So let's say we didn't rotate it, or rotated by 0. So the angle is 0 degrees, or just 0, so 0 degrees or radians, so it's all 0. So this is going to be equal to, this is going to be R of 0, which equals 2. Yeah, R of 0 times it by, and we know R of 0, that's just I. This just becomes the capital I. So the identity matrix times it by A. Like that, and this equals to B. Like that, so it's the same thing. So nothing changed. This equals to itself. And versus, let's move this here. Yeah, versus, shift that over. Or shifted that over. Let's move this here, and This is going to be our new axis. This is our x. This is our y. And now we're dealing with, well, if you have a like this, I'll make it, just make it bigger. So that's a. And now we're going to be rotating this by 90 degrees. So this is our new a. Like that. Let's make this a bit more steep. Alright, so this should be very, very similar. Alright, here, just fix that up. It's somewhat like it. And this angle, this is 90 degrees. I'll put a right angle there. Make this a bit better right angle. Alright, so it's a right angle. And this is theta equals to 90 degrees. And this one is 0 degrees. Just put that there just for completeness. Alright, so now that we have B, this equals to the unit identity matrix times it by A. So yeah, so this vector times it by that, we get that. So that is it. That's all it is then. Yeah, so the complex number as a rotation matrix is just shifting this by 90 degrees counterclockwise. And then the identity matrix just doesn't do anything, just leaves it as is. Alright, so now that we have this, and let's go further. So note that if we rotate by a full 360 degrees, degrees or 2 pi radians, we get back to where we started. So let's illustrate that. So we'll have, let's say we have it here. And if we have this, make this more horizontal, x, y, and we have a vector a, this a right here. And now we start off here. So we go by a full 360. So we go 360 degrees, like that. This equals 2 r, and then this is going to be 2 pi radians. Put it like that. 2 pi times it by a. Yeah, the matrix times it by a vector. This has to equal itself. This has to be just the identity matrix times it by a, which again, this is our b, so they all equal each other. And we can actually see this further by computing this or calculating it out. So note that r of 2 pi is equal to, well, put in our identity matrix, not our rotation matrix, we get cosine 2 pi, negative sine 2 pi, and then sine 2 pi, then cosine 2 pi. This equals 2. This equals 2. Let's put it over here. Let's go back up to our graph here. So at 2 pi should be somewhere across. This is a bit outstretched. This should be right here. Actually, 2 pi is there. And here, just quickly shift this over. Just fix this up. This is at 2 pi. So 2 pi cosine, sine is 0, and this one is going to be at 1. Is at 1 there. All right. Yeah, so then this is, cosine 2 pi equals 1, and this is sine 2 pi equals 0, like that. All right, let's continue back here and plug that in. So we get a 0, actually no, it's a 1. 1, sine is 0, cosine is 1. 1, 0, 0, 1, and this just equals to the identity matrix. Like that. And here I just boxed that in, and so note that, and also, let's just do we haven't done this calculation actually, but it's pretty straightforward. That's why it's called identity matrix. So if you have this right here, I times A, so if you have, let's say we have I times A, like that. And let's say this equals 2. We have our 1, 0, 0, 1. And let's say A has components x, y, like that. So we're multiplying by the identity. So then this row times by this column. So x times it. This equals to, well, x times 1. 1 times x is just x. Because then 0 plus 0 times 1. And this is going to be... this is going to have the same rows here. This is I is 2, this is I is 2, etc. And then it has n is 1 here, n is 1, n is 1, etc. I'm just going to erase these. So that's straightforward. And then the next one, it's only one column, so 0 times x is 0, plus 1 times y is y. So in other words, nothing changes. And this just equals to a. So multiplying by the identity matrix just gets a equals all this, and this equals a. So nothing changes. Alright, so now we've covered all this, and now let's do some interesting stuff with what we've learned. So reinterpreting Euler's formula. So now let's consider the famous Euler's formula by Leonard Euler, and reinterpret it as a 2x2 rotation matrix. So this is the famous formula. E to the ix is equal to cosine x plus I times sine x. And you can prove this using power series for e to the x. Plug in ix and then separate them, you get cosine x, sine x, and so on. I may do that. I'm not sure if I've done it or not in my videos, but it's pretty straightforward. Anyway, so this is the famous formula. I'll just box this in. And now write it over vs, write it in the different format. E to the ix, so we don't need to circle. E to the ix equals to, in notation format, in 2x2 matrix format, as a 2x2. This is all it is, cosine x, and then there's I sine x. So in other words, that's the imaginary component. This is the complex number, that's the real part, and that's exactly the complex number. And here, scroll all the way back up, so z equals a plus bi. Yeah. The Wikipedia just has the I in front, but they use that notation. But anyways, this is just a rotation matrix. Cosine x, negative sine x, and this is going to be sine x, and this is going to be cosine x. Like that. So yes, fascinating stuff. Alright, and now let's take a look at Euler's identity. I'll just write this formula, bold this one. So that's bolded. So when x is equals to pi, we get Euler's identity. And Euler's identity, well, let's write this here. So at x equals to pi, this is radians, equals to the same thing as saying 180 degrees, and yeah, degrees. So what we get is, for cosine pi, this equals to -1. Then sine of pi equals to 0. And we could see this from our trusty setup over here. So there's sine, and this is pi right there. So sine is 0. Sine pi equals 0. And then this one here is at the bottom there, that's cosine. Cosine pi equals -1. Alright, so we have those values, and now we can throw them inside our rotation matrix, and we get e to the I pi equals to cosine, well, actually before the rotation matrix, this is just the mainstream, or just the standard derivation. We're just using this right here for now. Alright, so e to the I pi, where x is pi, equals to cosine pi plus I sine pi. So in other words, this vanishes, it's 0. So this just goes to, 0. I'll just put this here. This equals to -1 plus 0. And this is interpreted as, well, we could move this over. Yeah, so what we get is basically e to the I pi equals to -1. Or you can move this over to the other side. And this is how it's typically written, e to the I pi. Or actually, here, I just erased that, move this over here. So move it here. And just write e to I pi. So move the 1 over here. So it would be +1. E to the I pi plus 1 equals to 0. And it's famous because it has all of the interesting parts there. It has an I, it has pi, it has e, it has 1, and it has 0. Alright, so a lot of interesting stuff here. Alright, and here, just move the arrow on top so it's easier and we could box this in. Alright, so that's what we have. E to the I pi plus 1 equals 0. So it's it looks elegant and so on, but I think the 2x2 matrix is more telling. Alright, so that's what we have, and I'll just put this vs, or actually instead of saying versus, we're not going against anyone else, write or, write it like this. So or in 2x2 matrix format, or in the rotation matrix format we get, or we could write this as e to the I pi equals to cosine pi times 1. First, just write it down like that. Plus, just write the notation we're used to. Sine pi times I. So just rearrange this. Put it here. Put the 1 there. And now this equals to negative 1. Yeah, negative 1 times, this is cosine pi is negative 1. Cosine pi is negative 1. So negative 1 times 1 plus the next one is 0 times I. So you could write it like this, so that you're talking about complex numbers. And then equals 2, and I switch it over into matrix format, identity matrix, plus 0 times it by, or just erase it times by, same thing. Or actually, I'll just leave it there. 0 times by I matrix, like that. So this is equal or equivalent to, let's put it just equal to, so we're switching it over. And now this equals 2, and what this equals to, this vanishes, so all we're left with is a negative of the identity matrix. So in other words, we're going to have a negative 1, 0, 0, negative 1, like that. And again, plug this into the identity matrix format, into the rotation matrix. Remember, this was just the cosine pi, which equals to negative 1. Negative sine pi, which is 0. And we have sine pi, and then cosine pi. That's what we have. So in other words, we could write e to the I pi equals to negative identity matrix. Yeah, just if you erase all this, just cross it all out if you want. But I think when you cross out stuff like this, you're removing information. So in this case, removing that, it's you're dealing with complex numbers. In other words, a two-dimensional number. You have multiple properties of it. So just a basic number. So this is like that. And if you shift this over to the other side, I'll put it on the top arrow. Move it over to here. We're not putting it into the exponent, just putting it here. Or just fix that arrow. So move it over to this side. We get the famous equation. Yeah, so e to the I pi equals negative. This is I matrix, or put it here. E to the I pi plus identity matrix equals to 0. Like that. Absolutely fascinating. Stuff like that. Yeah, and just for completeness, I'll put the negative side as well, because it's interesting stuff here. So equals to negative I. Negative the identity matrix. Like that. And similar to here, or e to the I pi equals to negative 1. Like that. Yeah, so in other words, e to the I pi is just a rotation matrix that rotates a vector by 180 degrees. So let's take a basic vector like here. So if you have set up here, and here's fix that up. So this is the x, this is the y, and you have, let's say you have, let's draw this thick line like this. Let's say you have an arrow that's on the axis. This is, let's say you have the vector A, like that. And here's the origin. And now it starts off from the origin, goes to here, and now you're going to rotate this by 180 degrees. 180 degrees is just equals to pi radians. So you're going to get a vector across to here. You're going to cross it like that. Whoops, same thing here. So basically you're going to go negative on it. And this is going to be negative A, like that. Yeah, it's negative A, and this just equals to negative identity matrix of A. I'll put this higher. It's going to be negative A, like that, which equals to negative identity matrix of A. Yes, fascinating stuff. So that's on the axis to make it a bit more visible. I'll put this like this. All right, so let's say we have an angle like, or a vector like that, x, y, and we're going to rotate this. So in other words, we're just going backwards. Hence that negative 1. It just means you're going backwards on this vector. So you're going backwards. This is 180. This is, yeah, going backwards by pi, and or just put 180. 180 degrees. And then this is, if that's A, this is going to be, well, negative A, which equals to negative the bracket I a vector like that. So yes, that is, and there's the origin 0. So this is actually absolutely fascinating stuff. And here I just move things around so that it all fits nicely together horizontally. Move this over here, and then finally, yeah, this one just equals to, again, this just it's like your, yes, when you have this negative this a vector, and this is equals to negative the identity matrix times by this times by a vector over here, and you're rotating it 180 degrees. It's again, this is, since they're equal, you're just multiplying it by e to the I pi times by the vector. So when you multiply that vector out, it's like shifting it over to this side. And basically, yeah, you're multiplying it by 1 then. Yeah, it's a negative I. So if you have a components like this, is, let's say you had 1, or let's say you had components A and B. Now you're going to go backwards. Now you're going to go negative B, or actually this one, A, B. You're going to have negative B, negative A. You're just going backwards. It's fascinating stuff. All right, now we're pretty much done the video, just the last section right here. So let's just keep going further. So application to other fields. So since complex numbers are applied to many different fields in mathematics and physics, including electromagnetism and quantum mechanics, reinterpreting such equations as rotational matrices may provide unique insights. So yes, try investigating yourself and let me know what you discover. So the same way that we changed up Euler's formula into a rotation matrix, is basically a 180-degree rotation. So yeah, so let me know what you discover for especially electromagnetism and so on. So finally, we covered 2D rotational matrices, but the concept is similar when dealing with 3D, which is something I may cover in future videos, so stay tuned. Anyways, that is all for today. Hopefully you enjoyed this. This pretty epic video. Is longer than I expected, but pretty in-depth. Just to illustrate the basically also to cover matrices and so on. And yeah, it's very interesting how you could view complex numbers as rotational matrices. Anyways, that's all for today. Hopefully you learned, and yeah, you can download these notes, these exact notes, and link in the description below, as well as viewing them as an article on the Hive blockchain, and the notes will be also in the article link will also be in the description below. Anyways, thanks for watching. Stay tuned for another Math Easy solution.